cosmology entails. Then I'll move to a few mathematical tools that you need in order to move to cosmology. Some concepts that will derive from relativity. Then I'll, of course, dive into the standard cosmological model and try to build the framework of this model. And finally, I'm trying to motivate you what the problem regarding dark matter is and what are the open areas of research in this field. Okay, so let's begin. Introduction. Okay, so what does the study of cosmology actually mean? According to me, it is basically, at the present, we have certain clues, certain hints, some observations, you can say, which we have obtained through data collection, measurements, detection and all. And we use all that set of clues and hints in order to figure out what the past of our universe was, and sometimes we try to predict what our future is going to be. This is basically what cosmology is. In this picture here, gives you a brief summary of whatever we have been able to figure out as of now. In the initial stage, we have the quantum fluctuations that actually kick-started the Big Bang. Then we have the period of inflation, a relatively short period, where the universe expanded at a massive acceleration. The acceleration was so great that even light couldn't keep up with it. Then we moved to the radiation-dominated phase, where all these nuclear reactions happened, or what we call the Big Bang nucleosynthesis. The second point. The Big Bang nucleosynthesis basically established all of those chemical elements that we see today. At the end of this Big Bang nucleosynthesis, we had something which we call the last scattering surface. You can understand it this way. During the Big Bang nucleosynthesis, there was this really hot plasma. It was filled with charged particles. Because of these charged particles, any photon that was moving about got scattered very frequently. So this early hot plasma was really opaque. As the temperatures cooled, these charged species, they started being captured. They started reacting with other charged species and formed neutral ones. Now the photon can move about freely. So this is what we call the last scattering surface. And at the last scattering surface, whatever photon disturbances or temperatures we had, this is what it formed the cosmic microwave background. It is one of the observables which we rely on so much currently. After the radiation-dominated era, of course, we had this structure formation, the galaxies started forming. The middle part of this diagram was a long time. Then we had this period of acceleration which we are at currently. The WMAP, it is a satellite which was the first probe of cosmic microwave background. So these are the key aspects of the evolution of our universe. We will discuss them in further detail as we move on. So now we move to some of the basic concepts of relativity. I'll try to inspire you what they are. First, we discuss something which is called a matrix. Okay. So to understand matrix, what you need to think of are coordinates. Coordinates are basically labels which you assign to every location of your space-time. So think of it this way. You have a 1D space. First, you need to pick some origin. This is let's say our origin. Suppose you had a rock here, you had a tree here. You took a scale, you measured the distance to the rock. Let's say it was 1 meter. This is 1 meter. And to the tree, let's say it was 3 meters. Now what I can do, I can place my labels, which are the coordinates. I can establish a coordinate system. I will say the rock is my coordinate position 1. The tree is my coordinate position 3. And of course the origin is coordinate position 0. So this is basically an exercise to tell you the difference between coordinates and distance, because up until 12, what we were used to was just the Cartesian coordinate system, whichever was 0.1, it is at unit distance, 0.2, 2 unit distance, and so on. But in this case, what might happen is that suppose we have this coordinate system established, and then the space around it started expanding, it started stretching out. It's not that he is rock or the tree itself is moving. However, the ground itself that you are standing on, the space itself, it is stretching out. So you are still at the origin. However, the rock which you have labeled with coordinate 1, it might move to some other distance. Let's say a distance P. And the P might move to a higher distance, which you had labeled earlier with coordinate P. It is about 5 meters. So, what is this quantity that actually relates your coordinate labels to your distance labels? So, this is what we define as our metric. This metric is the quantity that relates your coordinates to your distances. So, you can think of this makeshift equation as some sort of function. You give input the coordinate difference, it will spur out the distance between the 2 points. For example, in this case, what the matrix would basically do is, if you give input the coordinate difference, let's say 1, then it will give output as 1 meter. In the other case, if you give input 3, it will give the output as 3 meters. But in the second case, the matrix has of course changed because our space has expanded. If you give input 1, the matrix should be constructed in such a way that it should give the output of 3, not 1. If you give the coordinate difference input as 3 to the P, then it should give output 5 meters. So this is what a matrix actually does. It tells you at what coordinate, how do we calculate the distance at that coordinate, basically. Now, this matrix, as you can see, it will actually depend on what coordinate labels we have placed from the start. Of course, if I change these labels, if I make it 2 or 4, my matrix should also change accordingly. Now, what might happen after we have fixed our coordinate systems, after we have established our matrix for any of those cases, what might happen is that the space may still expand over time, because of which we need to keep updating your matrix. So your matrix might be time dependent. In the same way, your matrix can also vary from location to location. Just in this example, for the rock, the matrix set at coordinate difference of 1 gives you an output of 3. So the matrix function is valued at 3 for the rock. But for the tree, the coordinate difference of 3 will give you 5. So the matrix, you can think of it as being valued at 5 by 3. So the range changes from 3 to 5 by 3. So your matrix can of course change over time. It can change over space or the location. Okay, if this established, we now move to geodesics. So, what is the basic definition of the geodesic? A geodesic is the shortest distance between 2 points. Suppose you have your coordinate system established, your matrix established, you know how to calculate distances. So in that way, you have 2 points, and you want to figure out what is the shortest distance between these 2 points. Okay. This is not a normal Cartesian system distance. We have a matrix which varies from place to place. So you have to calculate distances accordingly. So in order to figure out what is the shortest route or curve between these 2 points, you can have 2 approaches. The first is called the variational method. The variational method is really simple. You take any curve that connects these 2 points, let's say point A and B. Okay. You can quantify your curve in this way. It's your curve C as a function of time. The given parameter is the x, the y, the z. This is how you make your curve. So, variation principle is basically this. You change your curve by small amounts each time. And you calculate what is the distance for each of them according to the earlier formalism which we established for the matrix and coordinates. Okay. After computing the distance, let's say S1, S2, S3, S4 for each of them, you minimize this distance. You can do your differential geometry thing. You can calculate the slope. Where does it minimize? From that, you can figure out for the shortest distance, which was the curve corresponding to it. Once you obtain that curve, that is your geodesy. Okay. What could be the other way? The most simplest answer that we know intuitively is the shortest distance between any two points is a straight line, of course. But how do we define a straight line? Where in a space where each of the points has a different measuring unit because the metric is different at different places. How do we define a straight line? From intuition, you can again go back and think about it. A straight line is basically such a curve where, in fact, each point construct tangent vectors. Like for this curve, if you differentiate in respect to time, what you will get is the velocity vector, which is basically tangential to the curve. So a straight line can be defined this way. A straight line is a curve where the tangent vector at each point along the curve doesn't change at all. It remains in the same direction. So that is how we can define a straight line. Even in a curve or a different stretching kind of a space line, this definition will still hold. So how do we construct this geodesy from a straight line? What we can now do is take any curve. Okay. Say we take this curve for example. For point A, let's say we find out its tangent vector T1, and some point after A, let's say B, we construct another tangent vector T2. So what we do now is take this tangent vector and move this vector along itself. Basically what we are doing is, we have this point A, we have constructed this tangent vector T1, we parallelly transported this tangent vector along its direction. So that gave us T1 and point B, and at point B we constructed the tangent vector corresponding to this curve, which might be T2. Now we check whether T1 and T2 are equal. If they are equal, then it is a straight line. If it is a straight line, then it must satisfy this property that between the 2 points it is the shortest distance. So these are the 2 ways. One is the parallel transport thing and the variational principle thing. Kind of intuitive ways, but they give us a really powerful tool to calculate geodesics in any space-time given the coordinate and the metric. Okay. Now the final thing that we need to take home from relativity. So up until now, I was talking entirely in space. So there was this x coordinate, y coordinate, and z coordinate. Now what we will do is, in addition to these 3 coordinate or coordinate axes, if you say, we will combine the axis of time. So in addition to the spatial one, let's say x, you combine another axis for time. Of course, the dimensions do not match, so you have to multiply factor of c. So this makes your entire 4-dimensional space-time, which we are going to use in general relativity. Okay. So time acts on equal footing with space in general relativity. And then, okay, so we can establish the notion of a matrix here. But what actually causes the stretching of the space-time? That is the first question that we should ask. Okay, because the space-time was stretching, we have to move to this matrix kind of formalism. But what actually causes the space to stretch? The answer is any massive object. This is what the Einstein equation actually tells us. Any massive object, if you place it in a space-time, it will change the metric points around it. Basically. So yeah, from this figure you can observe. First, there was, so these lines, the white lines that you see, these are your coordinate labels only. Once you place the mass, the distances, actual distances between these coordinate labels change. So this depression that you see here, it actually denotes what is the metric at that point. Okay. For these 2 points here, the distance might be 1 meter, but for the same unit coordinate difference closer to the massive object, the distance might be different. That's why it's a bit different. Same. So this depression basically means that the metric has changed around the massive object. Okay. How much it has changed? That is given by the Einstein equation. So Einstein equation is basically you give input the distribution of masses and it will give output the metric corresponding to this distribution. Okay, so now we know we have space-time, we give input whatever the mass distribution is, we compute the metric. Okay. So we know at each point what are the masses, at each point what is the distance. Now we are all set to reinterpret gravity in terms of relativity. Our earlier notion was that any massive object it exerts a force gm upon r square on any other test mass. So this force we can reinterpret in terms of this formalism that we already established. What we say or what we propose is a simple thing. All objects move in a straight line. This is all that we require to understand general relativity. Let me explain it a bit more. By straight line, I mean geodesics. So what you say is that you have a space-time, you have the metric, at each point you know the distances, at each point you know what is the mass. You construct the geodesics using the formalism that we already established, the variation principle of the straight line thing. You know what are the geodesic curves in this space-time. You say that whatever particle I have, they will move only along this geodesic. So this is in a way removing your force of gravity. So whatever the effect of gravity was has been transferred into the matrix itself. There was a mass, it was exerting force because of which the particle's trajectory was being changed. But now what we see is that there is a mass, it will change the metric around it. For that changed metric, we compute the straight lines. These lines will be straight only in the space-time, not in the space itself. That is what we need to differentiate. In this space-time, we compute what are the straight lines, and we say will move along these straight lines. So this is what we call the equivalence principle. Motion of an object due to gravity in a flat space-time, which is a general equation, is equivalent to saying that particles move in a straight line in curved space-time. Okay. So if particles actually move along straight lines in space-time, why do these trajectories like these photon orbits appear curved to us? This is because there are straight lines only in space-time. What we actually observe is merely a projection in the space dimension itself, not account for the time. So this trajectory, even though it appears to you as curved in space, is actually a straight line, geodesic in the space-time. Okay. So if you look at it now, it actually becomes much more simpler. We do not need to have another force. We do not need to have gravity. We just say particles will move in a straight line, which was Newton's original first law. Without, in the absence of any force, particles will move in a straight line. This is all relativity there is. Okay. So, any doubts up until now? Okay. So, with these tools established, we can now move to standard cosmology. So all are really allowed to ask me anything at any point. Only then we can move to the next part. So if it is clear, then we will move on. Okay. So now we will how do we build a model for cosmology given that all of the matter density whatever we have. So of course we know that our universe is not homogeneous. In a way we are saying that okay, there is a table here, but there is no table at that location. So universe is not actually homogeneous. What we do is we look at the universe on a large scale. If you look at the universe on a large scale, then large scale I think about megaparsec scales. 1 megaparsec is about 10 to the power 16, so megaparsec is 10 to the power 6 meters. About 10 to the power 22 meters in that scale. If you look at the universe, then whatever matter density you have in one volume, will have roughly the same matter density and another volume of the universe. So that's what I mean when I say that we assume our universe to be homogeneous. It's almost uniform. We also assume our universe is isotropic, like it is almost same in every direction. So with these two conditions, you can say that because the distribution of matter is same almost everywhere, then the corresponding matrix will also be uniform. So if our matrix is uniform in space, the only dependency that it will have is on time. So that's why our complicated matrix equation now reduces to a simple scale. We input the coordinate difference, we scale it by the corresponding matrix, just a scalar term, and that will give us the distance. And this is indeed the FLRW matrix, which you might hear in your future courses. And so now for the universe, at least on the large scales, we have established that okay, it is homogeneous, isotropic, we know the matrix, it is a simple scale. Now we have to fill in whatever particles or species that we had. So the first particle that we fill in is the dark energy. The next one is the dark matter. And the baryons are basically your protons, neutrons, these simple building blocks of all atoms. They form most part of the matter that we see. Then we have photons and neutrinos. Okay. So these particles we are familiar with, baryons, protons, neutrinos. But we do not know about dark energy, we do not know about dark matter. Yet we have introduced them in our model. We will see them used later on. So this dark energy has this property that it has really low energy density, but it fills the entire space. We do not know what particle it is, but we assume that this is some energy density which is ever present. And one more interesting thing about it doesn't change at all. It is constant flow. No matter what the volume of the universe you take, will have the same energy density for dark energy. So in a way, this dark energy, we model it as being an intrinsic property of vacuum itself. Then we have dark matter. It has properties similar to baryons, but it is invisible. I haven't yet detected any visible signature, any electromagnetic interaction from dark matter yet. Okay. So with these species, we have filled in. So we have the matrix, we have the distance index, we have the ingredients of our thing. We will fill the ingredients into the matrix. And this is a basic synopsis of how these particles were formed. So early in the universe, we had this really hot plasma. In this hot plasma, the temperatures were really high. These species interacted with each other through nuclear reactions. As the temperature cooled down, these nuclear reactions gradually stopped, and these species stopped interacting with each other. So after Big Bang nucleosynthesis, the number density of each of these species, the total number, got frozen out. So this is what Big Bang nucleosynthesis is basically. So now our final aim is to solve for two things only. The matrix, which is basically what will be the function for the scale factor A, and the distributions of each of these species. How do these distributions and the matrix, how do they evolve together? Baryons. So baryons are the simple building blocks of atoms, protons, neutrinos. In a more perspective from the standard model, these are 3 quark particles. 3 quarks we really want to make baryons. Okay. So how do we go about establishing the relationship between the matrix and the distribution of each of the species? There are two equations only. First, as we discussed, the Einstein equation. You plug in the distribution of each species. Basically, from the distribution of each species, you can compute the mass of each species, the density, the distribution of each species. You plug that in. From that, you can use the Einstein equation to solve for the matrix. So this is Einstein equation. This is all that it tells you. How do the species, the distribution of each of the species, how do they affect the matrix? How do they affect the distance calculations? Then, in the reverse cycle, we have the Boltzmann equation. The Boltzmann equation is basically your geodesic equation that you calculate from the matrix. So, to take your coordinate system, you plug in the distribution of each of the species. And using the Einstein equation, you calculate your metric. Once you have your metric calculated, you can use your geodesic equation formalism to calculate what are the geodesics in the given metric. Then geodesics will tell you how do these species particles actually move in your metric. So once you know that motion, then you can figure out how do the distribution of each of these particles evolve. So this two equations basically give you a coupled set, the entire set that you need to solve for to find out the metric and the distribution of each species.
Could you elaborate more on
Okay, so Boltzmann equation, as you can see, is this df by dt. So f is your distribution, phase-space distribution, phase-space whatever you tell. Okay, so the phase-space distribution will be equal to any of the scattering term that you have. Okay. So after you define nucleosynthesis, the number of each species were fixed. Now suppose you have your metric calculated. So how does the distribution of each of these species now evolve? Given that you have your metric fixed, you know the geodesic equation. So the geodesic equation which you calculate for your metric, you will have to plug that in df by dt. So once you plug that in, then you solve for f. So that is your Boltzmann equation basically. A bit more technical since last. So df by dt. Sorry. What you have to do is your f, your phase-space distribution. It might depend on the momentum of the particles, because it is phase-space distribution, the direction of the momentum, the position of each of the particles, and the time. So you do a differential calculus, you will apply the chain rule. So you will have terms like dq by dt and dx by dt and so on. These terms. You plug the geodesic equations in here. So that will give you the formal form for this equation. So this will be space distribution terms for f. You plug the geodesic equation, you equate it to 0. Solve for f. So this is your Boltzmann equation. Okay. This is not going to the calculation. Okay. This is all you need to take note. Einstein equation will tell you how the metric evolves according to the distribution. Boltzmann equation will tell you how the distribution of each species will evolve according to the metric. That's all. So on the right side you have plots for the solutions after solving these two coupled equations. As you can see on the y-axis, we have the scale factor A, which represents the matrix, because the simple scale for the large scale of our universal age. And on the x-axis, you have time. So this is a solution of how the matrix evolves with time. Okay. So for the first one, the purple line, you can see the scale factor keeps on increasing at a slower rate. It can start expanding at a much higher rate. So this tells you that our universe is currently expanding at an accelerated rate. This tells you that our universe is accelerating right now. For the other solutions, we have this blue line, which corresponds to it. Explain this a bit. So when solving these two equations, you get certain three parameters that you need to fix. One is your so this rho m is basically how much matter is present. Rho d is how much dark energy is present. This is the matter part. The matter part includes your baryons and your dark matter. Okay. So if you plug in these two parameters, then you can solve these two equations. These are the let's say your degrees of freedom in this equation. Okay. So for matter contribution about 30% and dark energy contribution about 70%, we get that our universe is accelerating. The same thing is said for if you have 20% of matter and you have no dark energy. If you have no dark energy, then your universe keeps on expanding, but not in an accelerated rate. It does expand, yes, but there is no acceleration. Then, if we have matter about 1, let's say 100% contribution, but no dark energy, we will have roughly the similar case that there is expansion, but there is no acceleration. However, for the last case, if you have 300% of matter. This percentage are scaled relative to the critical density. Each of the densities of each species, how do they evolve? So, early, can you see the plots? Not clear. One plot for the radiation part. The radiation includes your photons and nucleus. Then you have one plot for the matter part, and you have one plot for the dark energy. So up until this, so for some part of the universe, for some part of the time, let's say 60 time, for the early part of the universe, we had radiation domination. Then for this much time, we had matter domination. Then from that matter radiation equality, up until now, we have dark energy domination. So this is what the solutions basically tell you, that there were three. One was the radiation dominated, matter dominated, and dark energy dominated. Okay, so we have figured out the solutions, but how do we know which one of them is the correct one? For that, we need to match these models to actual data. So this is the data for the supernova SN1A. You might have done this fitting supernova SN1A fitting in the last Tuesday talk. So these star lines are actually the actual spiraling data points, and the black curve is the fitting according to the solution that you obtained from the background cosmology. And you can actually see the fit parameters. For the fit parameters, we have rho 8 about 0.7. So that actually matches the first model that we obtained from our solution. This one, 0.7 model. So after fitting with supernova catalog, we obtained that our universe is actually accelerating, and the total contribution. And the contribution of the dark energy is roughly 70%. Just take time to realize what this actually means. 70% of our total energy density that we currently see in our universe is actually unaccounted for. It is some sort of energy that we know permeates our universe, but we have no clue to what it actually is. The rest of the 30% is contributed entirely by matter. Okay. Then the radiation contribution is almost negligible. Also, up until now, we modeled our universe as being homogeneous. So each of these matter, photons, radiation, dark energy, these were equally distributed in space. So now you can ask, if they are equally distributed in space, how do we account for the structures that we see today? How do we account for the galaxies? These are not uniform. So where do the galaxies actually come from? How do these clusters form? For that, we might have to add one more thing. In addition to the background matrix and the background distribution, which we already calculated, we have to add small disturbances, small perturbations. So after calculating the background, we add the small terms like do an expansion of e to the power x, you get 1 plus x square and so on. So you can think of your background as being this value. Then you can think of your perturbation as being these values. They are really small values, but they account only for, let's say, 10 to 20% upon your actual background. So this is your first order perturbation, this will be your second order, third order, and so on. So what we'll do is take only this part, take only the background and the first order perturbation. Then we solve these Einstein and Boltzmann equations again. We know the solution for the background. The only thing we now need to do is solve for the perturbation. So once we solve for the perturbation, these are the kind of images we obtain. Really simple mathematical tool, but it gives a really complicated picture of a universe. The first one, these are the matter perturbations. Matter consists of, as I said, ions in dark matter These are really massive particles. Since they're massive, they can actually have this gravitational interaction. They can actually curve the matrix a lot. Because of this, they can clump together. They have really small velocities. They can clump and form these kind of structures. This is an actual n-body simulation after simulating these particles. So you can observe these small, very clumped structures in the orange parts. These structures are what will form your galaxies. These are the clump things that will form galaxies in the long run. And on the right hand, what you have are the photon perturbations, the radiation perturbations. This is a plot of the different temperatures that we observe at different angles. This is a stereographic plot. So on the y-axis we have theta varying from -90 to +90 degrees. And on the x-axis we have your azimuthal angle varying from -180 to +180 degrees. So this is basically your entire 4 pi stereo. On different angles you have different temperatures. Okay. So in the upper ones, the COPE, WMAP and PLAN, these were the satellite operations that were actually done in order to observe what were the temperatures at different angles. So this is what the right picture is what we call the cosmic microwave background. This is the most important data set that we have currently in order to fit models, in order to figure out which one is the correct. Okay. And what are the results that we obtain after fitting these models to actual data? First one, earlier as you might have realized, we only obtained a bound on the matter. This bound contains baryon plus cold dark matter. But after the perturbation thing, we obtained that the baryon fraction is only 5%. So out of this 30%, only 5% is contributed by our load matter. The protons, the neutrons, total they contribute only about 5%. So the rest of the 25%, these are actually contributed by dark matter. And dark matter is some sort of form, some sort of matter that is invisible to us. Again, we do not know what particles actually form dark matter, but we have only modeled them to be so. Next, we obtain the temperature of photons. So this temperature of photons can actually be converted into what the total contribution of photons is. And that is roughly 0.01% only. So radiation contributes really less to our current energy density. And the perturbations on top of this really less contribution is even lower, 10 to the power -5. So take time and really appreciate what sensitivity we have been able to measure them. Again, since we have obtained these photon perturbations, we can actually confirm that the last scattering surface actually existed. Because if there was no last scattering surfaces, the photons could keep scattering up until now. And because of this scattering, these perturbations would have been damped. Damped in the sense that one photon of higher energy carrying energy to a colder part might have evened out these perturbations. So these perturbations, we will not have been able to observe them had not there been a last scattering surface. So a mere observation of cosmic microwave background confirms that yes, there was indeed a last scattering surface, and it stemmed from the feedback nucleosynthesis calculations that we did. So the CMB confirms that yes, there was a period of early hot plasma. Then, okay, last thing that we need to consider is all of these calculations, they hold only at large scales. So this large scale calculation tells us that our universe was actually flat. There was no curvature to begin with on a large scale. But on the small scales, of course, we have these matter concentrations where the matrix might get curved. But on a large scale, since the background matter density, radiation density is almost uniform, our universe is largely flat. So this puts an upper bound. Using this, we can actually put an upper bound on what could be the neutrino contribution. Since our universe is flat, the total contribution of this should be 100%. So if we introduce neutrino on top of it, we do not want to exceed this 100% value. So then we'll put an upper bound on how much the neutrino mass can actually be. And from that we roughly figure out that the neutrino contribution is 0.2%. So these are the results that you obtain by just introducing perturbations. Okay.
If we really know the mass of neutrino particle,
No, we do not know the mass of the neutrino particle. We can only put an upper bound on the neutrino mass using using cosmology. If you really want to figure out, you have to go to quantum field. You can to understand the standard model and all. Using that, you can figure out. You cannot figure out if the calibrations have to be confirmed yet, but yeah, you can do the neutrino oscillations thing and figure them out. Okay, so a brief summary. We can return to the picture that we started with. Let us see if we have bettered our understanding of this picture. So the early inflation. This is what. Okay. So by doing the perturbation calculation, you might be tempted to ask where did these perturbations come from initially, because we only had modeled this background thing, which was homogeneous, but we arbitrarily introduced these perturbations. So one might ask, if there were no perturbations to begin with, then how could the perturbations have grown? So the presence of the cosmic wave microwave background with perturbations actually tells us that initially there were these perturbations themselves, and the inflation, the expansion, the acceleration only served to magnify these perturbations, and these perturbations then manifested as the galaxies, the structures, the microwave background, the temperature fluctuations, and so on. So in the early part of the universe, what we see are the quantum fluctuations which actually kick-started the Big Bang. These were the fluctuations that deposited these initial perturbations. Then these perturbations, they progressed through inflation. Inflation was a stage where your space-time expanded massively, massive acceleration stage. Then the Big Bang nucleosynthesis happened, where the numbers of each of the species were fixed. Then after the end of the Big Bang, the perturbations which progressed through them, they were deposited at the last scattering surface. And after the last scattering surface, the photons, they carried these perturbations to us unimpeded, they free streamed to us. There was nothing to stop them. That's why we are observing the cosmic microwave background today. So cosmic microwave background is basically a modified snapshot of Big Bang itself. Because Big Bang is the one which started these perturbations. That is what we are observing through the satellites today. So the presence of cosmic microwave background actually confirms that okay, there was a Big Bang. Okay. And the next part, after the radiation, then we had this radiation dominated era. Then from the background plots I made earlier, after the radiation dominated era, we have the matter dominated era. Matter dominated era is where your galaxies started forming. The matter perturbations actually grew in size. That's how the galaxies and other structures formed. Then, after the formation of galaxies, we entered the dark energy dominated era, the last part, which is where we found this acceleration. So we can attribute the current acceleration to the dark energy component of the universe. And the final summary of the lecture: universe on a large scale is flat, homogeneous, and isotropic, but not at small scale. Small scales, of course, we know there are galaxies that have fluctuations. Contribution of each of the species: dark energy, cold dark matter, baryons, massive and massless neutrinos, photons, decreasing order. So from this table, what you can observe is that the dark energy and dark matter together contribute 95% of our currently known of our current energy density. So 95% of total energy density, we cannot explain it. We do not know what 95% of our universe is. We are only playing with 5% of the energy density that is available to us, and we are doing a lot of physics. So we can just imagine what the other 95% of our universe actually holds for us. So that's how we are motivated to study dark matter. We are trying to figure out what the rest of the 10% is. Brief summary of what dark matter is. Of course, its total contribution to properties of dark matter. Of course, its total contribution should be 25%, and it should turn non-relativistic or pulled by matter radiation equality. This is important because dark matter forms 25% of the total matter density, and matter is responsible for your structure formation, galaxies and all. So in a way, dark matter is the key component to form your galaxies and other structures. So it should have been non-relativistic by matter equality, because had it been relativistic, it would have so much velocity and it would not cluster, it would not come together. That's why we need dark matter to be non-relativistic. And the third point, we want it to be electromagnetically neutral. This is because we haven't had any visible signatures of dark matter as of yet. Then dark matter can be classified into three types based on the process: cold, warm, and hot. Cold is of giga electron volt mass range, warm is of 0 electron volt, and hot is of electron volt. Then the temperatures, of course, the hot one has much more temperature than cold and warm. Then the velocities, the cold has the least velocity, followed by warm, and then the hot one. And final point is the important one. When do these dark matter turn non-relativistic? Cold one, since it is massive and has the least velocity, it remains non-relativistic all in all. The warm one has an intermediate mass, intermediate velocity. It turns non-relativistic just before the matter radiation equality. The hot one, it turns non-relativistic only after the matter radiation equality. So using this property and this requirement, you can actually rule out the hot dark matter. This is because the hot dark matter has too much velocity that it won't form the required amount of structures in the galaxy that we see today. So that leaves us with cold and warm dark matter to study. So this is what my area of interest is. I study warm dark matter. My supervisor is Dr. Shikhe Sethi. He is from Government Research Institute, Bangalore. Currently, my work is mostly focused on the warm dark matter. We are studying it through a built decay mechanism. I'll just give you a brief overview of my work. We first established the IISER-Mohali models. We worked out this drawbacks. Using those drawbacks, we were motivated to take up this warm dark matter model. We proposed a mechanism, we proposed its perturbation theory, and the predictions that we had from this theory, we managed to apply cosmic microwave background data. And from that data fitting, we were able to obtain mass and transition and other properties of warm dark matter. So even though we do not know what this warm dark matter particle actually is, but we know what its mass could be, what its interaction cross section could be, and a few other properties as well. So this is all. I would like to thank you for taking the time. Any questions?
Have you really observed the warm dark matter, or we are just observing like in matter only the cold dark matter?
Haven't yet observed the cold dark matter as well.
Yeah, not
Yeah. Yes.
but due to the minor interactions. And
Yeah, so detection experiments are trying to detect any sort of dark matter. They are through these interactions itself. Just you can think about it. What interactions can the dark matter show? Of course, it will show gravitational interaction because it is massive. Then no electromagnetic interactions, so that leaves us only two possibilities. Electro-weak interactions, strong interactions. Strong interactions, the cross-section, you can actually limit the cross-section of the interaction of dark matter through theory, which we did. And that actually rules out the strong interaction. So that leaves only weak interaction and gravitational interaction. So using these two interactions, you can figure out experiments to possibly detect. You can't directly observe a dark matter because no light is coming from it. But through other interactions, you can try to detect. There were three experiments like that for detected. One used its gravitational interaction. Then the other used its electro-weak interaction property, the LHC large hadron collider. It tried to actually produce a dark matter particle. Then there were these annihilation experiments where you hypothesize that the dark matter particles will actually annihilate each other and give off radiation. So you try to detect that radiation. This is how the detection scheme actually works. But none of these experiments have been able to detect any sort of dark matter. They've been only able to place constraints on the cross sections of interaction. That's or better progress that has been made. That's why you see a lot of these things gold, hot, hot. Once more data comes in, more things will be developed.
I had a question about mass. While measuring mass, we saw that the mass will derive electron.
For cold down.
How does that work? From what you know, basic understanding of electron volts and mass.
That is MC converts into energy. So yeah. So either electron volt. So this is mass energy equivalence basically. We take mass in kilograms and whatever, multiply a factor of C square, we get electron. But how much mass volt meter actually has, that comes from your data analysis.
So why do we use this instead of like, I mean, if this is simply a grade, like if this is mass energy equivalence, why do we use energy instead of like mass?
It's a bit more convenient because in terms of detection experiments, you start with what is the energy of the particle, what is the rest mass of the particle. The mass that you measure could differ in so you basically start with how much energy you gave to the particle total, the rest mass, the kinetic energy. So if you had it in kilograms, you have to convert again into mass. So just for convenience, knowledge, total energy assigned, start the collider experiment. That's all. Universes? Yeah. So yeah, that's what I'm trying to explain. So earlier when we had this picture. Yeah. So if you place a massive object, the matrix around it will change. So earlier the matrix was completely flat, equal at all points. You place a mass, around that mass the matrix will change. So this change in matrix is what we call curvature. Okay. Around a massive object, the space-time will have some sort of curvature. Okay. But for the universe at a large scale, we assume that the matter, the mass is equally distributed. So if it is equally distributed, then at all points it will have equal curvature. So equal curvature is a better way of saying flat. For large scale, our universe is flat. But if you go close to a massive object, of course you will observe some curvature. So that's what I mean when I say that our universe is large scale. Only on large scales you can see that our universe is flat. But close to a massive object, you will observe some curvature.
Would it not subside the theory of Wormwood?
Wormwood, I yeah, that's what I said. Around a massive object, you will observe curvature. Universe is not flat everywhere, only on large scale. So if you go close to a massive object, it is actually a smaller scale. On the smaller scale, you will have some curvature. That's why you observe black holes as well. The universe was completely flat, then there will be no black hole. You can understand wormholes and black holes in terms of the geodesics. Around the black hole, at any point, if you start doing the geodesics, then there will be no geodesic that will escape out of the event horizon. So there is no way for a particle to actually move out of the event horizon. And for the Bible, the wormhole to understand it similar geodesics.
Are there collider experiments going on to detect
Yeah, collider experiments are going on to detect the particles. They use the relativity.
How much capacity do we need to actually have? Is it actually have some sort of
You can take it this way. Just show one. Okay. Collider experiments. They will. Okay, so the issue with collider experiments is this. So they start with proton-proton collisions, really high collisions. So once these protons collide, they break down into their smaller bonds and all for a short period of time. So you know the energy mass equivalence. So some part of their mass actually gets converted into a non-visible form. So it could, that non-visible energy that we get, it could either be dark matter or it could be something else. So it is not a direct detection of dark matter. We are only assuming that whatever mass gets lost into this non-visible signature could be dark matter. When we try to compute what the dark matter contribution to this non-visible energy could actually be and try to match them. If it matches, then it is dark. If it doesn't match, it is strange. It could be some error as well. There was someone?
So in the beginning of the lecture, you said there was an incubation period in the universe where it expanded so far that light couldn't keep up. But in general relativity, we think the speed of light is the absolute, like nothing can surpass the speed of light. So why is it?
So that was to be more specific. In a local inertial frame, nothing can surpass the speed of light. Okay. These are not inertial frames, these are accelerated frames. The space-time itself is expanding. So even now there are galaxies that are really distant from us. You will have this Hubble velocity kind of thing. They are really distant. So it is not that the galaxy itself is moving. Our distance to the galaxy is expanding because of the space-time. So if you take that distance and find its time and compute the speed, that galaxy's speed will actually turn out to be greater than the speed of light. That defines your Hubble sphere. So the speed due to this expansion is something different from what we observe in our day-to-day experiments. We establish a local inertial frame, we actually move the particle. This motion of the particle is not due to the expansion of the nucleus. That is something different. This is something different.
How can you measure the temperature of photons?
Yeah, this can be done in a number of ways. Like for the photon distribution, you have this law. So what you do is you observe the photon, you compute the spectrum. You might have heard of this black body spectrum. You fit the spectrum to the corresponding Planckian for the temperature. So for the temperature which fits to the spectrum gives the temperature of the photon. Clear on this? Okay, again, the photon distribution is a black body distribution. The cosmic microwave pattern is a black body distribution. Okay, so black body distribution follows this kind of a thing. This H, you might have seen this from the black body distribution. So you take this curve and you fit it against the data. This is the data part. Okay. You fit these Planckians all along. For whichever temperature your Planckian distribution matches the spectrum, that gives you the temperature of the photon.
So you mentioned something about dark matter decay and cross section.
Decay.
Yeah.
BIM decay. Okay, that is actually the title of my project. So this is a mechanism by which warm dark matter can be produced. BIM decay basically tells you there is a massive particle, it decays and gives off a smaller particle. So this decay will impart some more energy to this smaller lighter particle. So that will come into the category of warm dark matter, which is some higher velocity. So decay is only a mechanism to produce warm dark matter. So this is the mechanism we are working on.
Has this been observed?
No, this is only my research project. Those are not a scientist.
And you mentioned also something about cross section.
Yeah, cross section. So every dark matter particles, every particle has an interaction cross section depending on which type of interaction it shows. There is a weak electroweak cross section, there is a gravitational cross section, scattering cross sections and all. This is how cross sections are associated with dark matter.
So it's different ways of interaction.
Yeah. The greater the cross section, the stronger the interaction of the dark matter particle to that mechanism, whether weak or strong or gravitational response.
You said that some hydrogons run into the particle. That is related to something for a higher dimension.
Okay, now the question is
During the collision experiment, some matter gets into this particle. So is it related to that the matter is going to higher dimensions?
actually we do not talk of this higher dimension. We are working on the display. The string field and all, we haven't get that right. At time has confirmed of 4 dimensions. We are spatial participating temporary dimensions. The other dimensions come from really small dimensions which are hidden of the string field and all. But gravitational waves